In the last class, we stopped deriving the equilibrium equation. We said that the equilibrium equations are similar to what you have studied in your earlier classes on, say, engineering mechanics, and sigma f is equal to 0 was one of the equations. We said there are two equations, sigma f is equal to 0 and sigma m is equal to 0, and we said we will concentrate first on sigma f is equal to 0. Before that, there were one or two questions which I think we should get to know the answer, because they are quite an interesting question was there initially before we just ended the class. So what was the question? Now I have two tensors, say sigma and delta, the two tensors. Now I actually operated on these two tensors and said that I get a scalar. If you remember, I said that sigma ij delta ij is equal to sigma ii. Okay? In other words, I operated on these two tensors. The question is, what is this operation and what are the types of operations that are possible, and what is the result? Is it that when I operate on these two tensors, I will get only a scalar? The question is very much valid because I said that these can be also looked at as a matrix. So if I just say multiplication of matrix, I should in fact get another matrix or another second order tensor. So this is the understanding. Yes, you are correct, but the only difference is that there are number of operations that are possible with two tensors. Okay? This operation, for example, is called as a dyadic operation. Now what is this operation? Let us understand this, let us not get confused about it. Suppose I have two vectors, let us go from what we know. Suppose I have two vectors, say u and v. All of you know that I can do two operations with u and v. A dot product can be obtained, which is say u dot v. Right? And what is this? What is the result of this? Scalar. What is that you do here? Actually it is u1 v1 plus u2 v2 plus u3 v3. And how do I express this in integral notation? ui vi. So one operation with two vectors gives me a scalar. Let us look at another operation. Let us look at this operation. What is this operation? Cross product. So what is the result of this operation? What is the result of this operation? Another vector. So by operating with the same vectors, on one hand I can get a scalar, on another hand I can get a vector. We saw how to express this also in terms of integral notation yesterday. So similarly, you can look at a number of operations with tensor also. Now what did we do here? Actually you have ui vj. Okay? I made j is equal to I in order to get the scalar product. Right? In fact, it is not that there are only two operations with vectors. I can have another operation called u dyadic v. Okay? The result is a second order tensor. the result is a second order tensor. The second order tensor, say for example, let me call this as say some tensor say C, okay, where this operation indicates that Cij is equal to Ui Vj. Cij is equal to Ui Vj. So you can see that before we proceed to this first equation, you can see that with the same two vectors, I can get a scalar by operating it, by operating it with another symbol and another rule, we get a vector, and yet another operation gives me a second order tensor. Okay. Now the question is, what are these operations? What are you trying to do here? These operations, okay, in later classes will mimic certain physical phenomena. In order to understand what this means, this particular operation means, you can look at, for example, force and displacement. So if you want to get, say, work done, what will you do? Yeah, so you will look at dot product. So you would see that when I have these vectors, especially in this course, with the physical meaning, okay, particular operations will give rise to certain physical quantity or phenomenon. Okay, this is independent of the tensor analysis and so on. But for engineers, it is easier to say that this dot product between these two vectors gives me this quantity, cross product gives me this quantity, and so on. Is that clear? Okay. Now coming back to this equation, in the same sense that I can have different operations, okay, I can have different operations defined on a second order tensor as well. Now this has sigma I j delta say KL. So I can get a fourth order tensor by an operation which is called as a dyadic operation. By a dyadic operation such that IJKL, say let me say this result in say D. Let me say that this results in D, such that DIJKL is equal to sigma ij delta KL. Is that clear? So whenever I put this operation, due to some say physical phenomena that is taking place, the result will be a fourth order tensor whose components will be given by this operation. Okay. After all, vectors, tensors and other things that we are going to use has some physical meaning, right? Stress has, we understand stress, even though I defined it very rigorously, we know what is stress and what it means and so on, right? This kind of intuitive feeling you would have developed already in the previous classes. Now the question is, why are you defining so very rigorously all this kind of things? Why are you now taking us to a tensor? Why are you defining stress as a second order tensor? Okay, this is another question. Why do you want to define it? Why not we stick to what we know as a matrix? Now this takes you to a slightly higher mathematical plane. What is that? And that is going to form, that kind of plane is going to form the basis of your further understanding of subjects like this. What is that plane and what is that understanding? Now when I prove or show that stress, I have not yet done it, okay, that requires some more rigor, but nevertheless when I show that the stress is a second order tensor, I am bestowing on that certain qualities of a second order tensor. What does it mean? Now if I keep defining sigma as a second order tensor, epsilon is a second order tensor, epsilon dot is a second order tensor, and so on, a number of quantities, That means that these guys will take the qualities of a mathematical say understanding called tensor, or mathematical definition called tensor. A second order tensor has certain properties independent whether it is stress is a second order tensor or whatever it is. It has certain properties. It has certain eigenvalues, okay, eigenvectors and so on. Okay. So, all these things will come to the second order tensor. Okay. We are going to see in this class, or maybe I hope it is in this class, that we are going to see principal stresses, how they are defined. You would have studied it in one fashion, but once I define second order tensor is the one which is going to characterize my stress, then I can say that these are nothing but eigenvalues of this tensor. I need not go and study principal stress, principal strain, principal so on so, as long as I say these guys are second order tensor. So, they inherit all the properties of a second order tensor once I define a physical quantity to be a second order tensor. When in the same sense that when I say vector, immediately you would go and tell me, or you would tell me immediately that a vector has a magnitude and direction. What is that you have done? So, in other words, what is that we are looking at? If when I say displacement is a vector, or velocity is a vector, or force is a vector, okay, what is that I am doing? I am saying that these quantities will follow the rules of a vector. These quantities will follow dot product. These quantities will follow cross product and so on. Is that clear? So, once I say these things, I need not worry about saying or looking at rules for these operations. Is it clear? Okay, fine. So, one of the operations will give me, okay, what is called as a fourth order tensor. Another operation called contraction operation okay, where I will make say two quantities to be the same, say I and k to be the same, or j and l to be the same and so on, okay, will give me a second order tensor sigma ij delta jl, which means I imply a summing up about j. Let us not go into the details because you can very systematically define what is called as transpose and so on. Okay, let us not worry about that right now, so that we don't deviate too much away from what we are doing. But nevertheless, since this question was asked, you can see that I can now define, okay, a contraction called contraction operation on a fourth order tensor. What did I do? I simply said, let me give a rule to you by making two of these indices to be the same. As soon as I define this rule, I also follow all the summation notation, which means that the resulting operation or the resulting quantity is a fantastic, it is a second order tensor. Now, I can give you one more rule. Next rule is that take the trace of this second order tensor. Okay, that means that second order tensor is a matrix, sum of the diagonal terms. What does that mean here? That means that make the other two quantities, other two indices also to be the same. So, I can say sigma ij delta ji. Okay, that is another operation. Another operation. Is that clear? Okay. Now, you will see that why am I doing all this? Why is that this becomes important? You will see that like we had a what is this force and a displacement to define what we called as a physical quantity work. Okay. I am going to say that I will operate with sigma and epsilon or epsilon dot rate of strain. I am going to define strain maybe in the next class. with if I go into if I can operate with these quantities, okay, I will get some other physical quantities, like for example stress, power. Okay, these operations we will carry out later will make use of such operations with the tensors. Is it clear? So there are a number of operations with tensors. In the same fashion, they are nothing but an extension of what you already know as operations with vectors. Clear? Okay. Now we will come back to this topic after some time. But we will get back to the problem which we were dealing with in the last class. Clear? Let me recapitulate this problem. We were trying to get at the equilibrium equation. We had said that there are two types of forces. The surface force has resulted in a stress, okay, or what is called a surface traction, right? And body forces. Body forces is defined as F per unit volume of the body. If it's going to be defined per unit mass, then you have to correspondingly bring into account the density of the body and so on. Rho F has to be brought. Okay, so this is the equation, and that is going to be equal to 0. Okay, we had defined this in terms of an indical notation as well, and said that okay, that's how we had written it in terms of indical notation, right? We also said that we can replace F, T in terms of sigma, so that this term can be written as sigma ji nj. Okay, the next thing, that's where we stopped in the last class, we just summarized it. And next thing we said that we want to replace the surface integral by means of a volume integral, and we want to use divergence theorem, right? That's where we had stopped. And what is divergence theorem? We had already defined what is divergence theorem. Okay, we say take a quantity phi I comma I dv is equal to surface integral phi I ni ds, right? This is what we had talked about the last class. I had already said that this comma means it is differentiation with respect to xi and so on. Now applying this equation to my last step here, okay, in this equation, the last step of the previous equation, for this place, at this place, what do I get? Sigma ji nj, okay, will become now, what is that it will become? Sigma ji j comma, that is important, comma j, now volume integral dv plus integral v fi dv is equal to 0. Okay, bringing them under one case or one integral symbol, I can write this as sigma ji comma j plus fi dv is equal to 0. Is that clear? Okay. What is that you learn from this? What is that you learn from this? Or what can you conclude from this? Look at this equation carefully. Now, it means that, obviously it means that the whole body is under equilibrium. Now, when I say whole body is under equilibrium, if I take a small chunk from this body, and apply this equation, it has to be under equilibrium. So in other words, this equation has to be valid for arbitrary volumes of the body. I take small volume, I substitute it in terms of traction forces, this has to be valid, right. So this has to be valid for arbitrary volumes of the body, or in other words, this has to be valid at every point of the body. I can consider infinitesimal volume around a point and say that I take this out, apply the same procedure, I will get the same equation. Is that clear? So for every infinitesimal volumes, or at every point that you can define, this equation has to be valid. So what does that mean? That means that when this total guy is going to be 0, it is not 0 on an average sense. It is not 0 in an average sense, but it is 0 at every point. In other words, 0 because this chap here is going to be 0 at every point. Or in other words, I get sigma ji comma j plus fi is equal to 0. Is that clear? Okay. So that is the equation which actually I get by considering equilibrium equation, or by considering the equilibrium, and it's called as an equilibrium equation. Please note that I started with sigma f is equal to 0. How many equations are there, by the way? There are 3 equations. Correct. There are 3 equations. Please note this carefully. Students tend to make a mistake that this I is not a repeated index. This I is not a repeated index. This I sits in one part of the term, this I is another part of the term. So the repeated indices are valid only if it is grouped like this. Is that clear? So you should not say that this is one equation because both j is repeated as well as I is repeated. Because please note, ultimately the summation operation signifies an tensor operation. Summation operations signify a tensor operation, right. Hence, this means that I have to apply I is equal to 1, I is equal to 2, I is equal to 3, and of course, the summing up is valid for j. So you can say that when I is equal to 1, I get, what is the type of equation I will get? Dou sigma 1 by dou x1 plus dou sigma 2 by dou x2 plus dou sigma 3 by dou x3 plus F1, which is the body force in one direction, equal to 0. Is it clear? Okay, like this you can write down 3 equations. This is the equilibrium equations, very, very fundamental equations. What all you do is to solve this or a variant of this. You either solve this directly or a variant of this. Okay? Through that procedure only, we are going to get stiffness matrices and so on. Okay? Fine. Let us now look at the next part of the equilibrium equation. Just to recapitulate so that you are not lost in this whole thing, what all we have been doing. Okay? Please note that we started, where did we start? We started with a small anomaly in the definition of stress which we know. Okay? We had in all our earlier classes or in the beginning classes of your engineering, you would have learnt stress to be force per unit area. We thought or we saw that there is an anomaly between them, between that definition and the result what you saw in the first class. And hence we started defining stress. We defined it much more rigorously. We didn't compromise on your understanding. We said, yes, your understanding is right, but I have to define that in a slightly more rigorous fashion. Hence, I define stress, okay, taking a point and taking a plane. From that, we define state of stress. From that, we came to equilibrium equation. One small factor is left. In fact, I am going to do this derivation not because it is very difficult and though the result is extremely important, okay, I can do that in a much less rigorous fashion, but I'm going to do this in a very rigorous fashion, basically for you to understand the use of indical notation. Okay, there's going to be small jugglery here and there, and hence that will enhance your understanding of the indical notation, and hence I'm going to do that only from that point of view. Right? We will come back to this figure now and put a small say add some things which we have not done right now. I hope any questions on this? Is it clear? Okay. Now let me add to this figure what is called a position vector. Let me define a position vector, say to that point, to be say r. Right? What is r? A position vector, which means that it is defined by means of x1, x2 and x3. They are nothing but the coordinates, right, of that point. So that is a position vector. Now what is that I'm going to do now? I'm going to say that sigma m is equal to, sigma m is going to be 0, and what is the effect of sigma m? What is the effect of sigma m? That's what I'm going to do now. Now how do I do that? What is that I'm going to do? I'm going to take a moment, okay, about say the origin. Okay. So what is the result, or how do I take the, what is the moment, or how do I get it? By defining the cross product. Now you see that there is a vector operation called cross product which you are using because you have understood what is moment, and when I do cross product I will get this moment. See, a lot of difficult things are simple, are made simple by taking a cross product. So once you understand what is a cross product, you can take moment without much problems. Okay? So this cross product is associated with this kind of, okay, activity determining moment or physical phenomena. Okay. So let me write that for the body forces and then for the surface forces. Okay, that's equal to 0. Yeah, any question? Right? Now let me express this equation in terms of indical notation. What is the indical notation we had used? Please note that carefully for cross product, or please look at it. What is the indical notation that we have used? Correct. Fantastic. So epsilon ijk here rj fk dv, right, plus same thing epsilon ijk rj tk n ds is equal to 0. Tk is the stress vector. Now I want to replace this by our stress tensor. You know the operation I'm going to do, same thing as what we did before. So what is that I do? So this this quantity, I'm going to replace this by sigma. How do I write that? How am I going to write this? That is the crux of this whole thing. Can I let me make a, I would say, mistake. Can I write this as sigma jk nj? Can I write like this? Because tk, immediately you have a tendency, because I've been using j there. So immediately, remember we wrote Ti is equal to sigma ji nj. That's how we wrote. right? So when I say k here, immediately the tendency for students is to write j, k, and j. That will be the tendency to write. Okay? Now you replace it with that. So let me replace that with that. Let's see what happens. Sigma j k n j ts. This is n. Look at that equation. Does it appear nice to you? Does it appear nice? What is the problem? Fantastic. So j is repeated. I'm not very happy with that, or it's not the right way to do things. I know that these two indices have to be repeated, and I know that they are dummies sitting there, and I also know that if I use any other index, okay, I will mean the same thing. So what is that I do? I'm saying that this is wrong, and so let me replace it with another index, say L. Okay, I hope it's clear. NL ds is equal to 0. NL ds is equal to 0. Any questions? Yeah.
How is it j repeated, sir? It's in a different variable.
Yeah. How is j repeated? See, when I put j here, it doesn't matter whether it is in a same variable or independent variable, as long as they are in the same conglomeration. Okay. For example, we said sigma ij, delta ij, or ji. Okay. When they are in the same conglomeration or same assembly, to understand that, okay, then I said that you have to add it, because j gets repeated. Is that clear? Sigma ji delta, sigma ij delta ji, or delta ij. I said you have to add it. Sigma ij epsilon ij, you have to add it, or sum it up rather. Summation notation is valid. So it is not that the summation is valid only if it gets repeated, okay, for the same variable or the same tensor. It is not that sigma ij should become sigma ii. Right? Is that clear? Okay. Say for example, ui vi. I gets repeated in u and v. The result is a scalar. Right? Same fashion, here it does not matter where it gets repeated. So it becomes epsilon ijk rj sigma lk nl. Looks quite complex, but once you understand, it becomes very easy to understand. Is that clear? Okay, take a minute and look at this, okay, and see what is the result of this kind of operation. What are, in other words, what results from this operation? What are the fellows who get repeated there? K gets repeated, J gets repeated, L gets repeated, and what is that ultimately you have? I. So which means that what is it? It's a vector. Okay, that is the result of a cross product. Is it clear? Yeah? Okay. Now we go ahead and apply divergence theorem to this particular part of the equation, because I want to convert the surface integral into volume integral. Okay? So let's write the first step here. Integral epsilon ijk. I'm going to again, be aware. I'm going to ask you a question. I'm not going to write that, so that you become familiar with it. Fk dv plus, let's see what you have to offer to me. Where, how am I going to write this? How am I going to write that? Because of the fact that, okay, this differentiation, differentiation with XL, okay, doesn't give me, it is 0. So I can write this as epsilon ijkl, sorry, ijk rj, no, both of them are there, no? Both of them are there. So rj, correct, sigma lk comma l. Right? dV is equal to 0. Is that clear? Yeah? Oh, sorry. Right. Okay. Let me bring them together and see what are the things that I am going to get out of it. So let me write this as V epsilon ijk into rj into, okay. So I have to differentiate this rj comma l sigma lk plus rj sigma lk comma l. So the first part I am taking, okay, rj into sigma lk comma l plus fk, okay, dv we will put it at the end, plus sigma lk, correct, rj comma l, the whole thing, dv is equal to 0. Is everyone with me? Is it clear? Right? Okay. What does this give me? Look at, I mean, actually we have done quite a complex operations. I think now it's so very logical and straightforward. I don't think there's any difference, I mean difficulty in this. Okay? Right? Is it clear? Okay. Now look at that and tell me how I can simplify this. How I can simplify this? What is the first term? That is the first term is 0. Why? Because it's the result of my equilibrium equation. Very good. I want you to participate because then you will understand whatever we have done. Fantastic. Okay, so this term goes to 0. I have only this term. Now let me look at that term rj comma l. What is rj comma l? No, dou r1 by dou x1 or dou r1 by dou x2 and so on. So what would be the result of this? What would be the result of this? No, no. Please note this carefully. What is r? R is nothing but the position vector. Position vector. Okay. So position vectors consist of r1, r2, and r3. Note this. Okay. r1, r2, and r3. r1 corresponds to the position in the x1 direction, independent of x2 and x3. So there are, in other words, in this Euclidean space, we need 3 quantities to define: r1, r2, and r3. So r1, they are all independent. So r1 is a quantity which is independent of 2 and 3, 2 independent of 1 and 3, 3 independent of 1 and 2. So what is that I will get out of this? So what are the quantities that are involved here? They are, say, dou x1 by dou 1, which means j and l is 1, dou x1 by dou r1 by dou x2, dou r1 by dou x3, and so on. Right? So since this r, it depends upon only the corresponding x, So what will be dou r1 by dou x1? That will be 1, right? But dou r1 by dou x2 0, correct, because it is independent, right? Okay. So many people what they do is, I mean, which may be also easier to understand, is instead of x r they will write x also, or in other words the position vector x will be written as xi ei. Okay, I didn't do that in the beginning because it may be slightly confusing, but I think now it will become clear, so that when I now differentiate, okay, dou x1 by dou x1, okay, it will be 1, and x1 by x2 will be 0, and so on. Is that clear? So that is also, it's also a nice way of looking at it, right? The whole thing comes from the fact that these coordinates are independent. Is that clear? So if you want, you can replace it, this r, by x as well, so that you don't get confused. Okay, I hope you understand that, and you can replace it by x as well without losing the understanding of what is position vector. Okay, so this term now is equal to, how do I write this now? So xjl is equal to 1 when j is equal to L, and is equal to, fantastic, 1 minute, and equal to 0 when j is not equal to L, right? Is that clear? Fine. So this is equal to delta JL. Is everyone with me? Is it clear? Okay. So this xj comma L is equal to delta JL is one thing where you will repeatedly be using in mechanics. Lot of places you will use this. Comes from the fact that x1, x2 and x3 are independent quantities, and x1 depends upon only the corresponding x, okay, and so on. Is that clear? Okay. So extending my same argument like what I did in the last derivation, that this chap, this fellow who's inside, has to be independent of the volume which I am considering. This term inside the bracket has to be equal to 0. Okay, whatever term that is inside the bracket has to be equal to 0, this bracket. So what is that I will get out of this? I will say that epsilon ijk sigma, what is, okay, before we proceed, what is sigma Lk? Okay, let's simplify this. Sigma Lk x j comma L, what will that become? This is delta JL, delta JL, this is what we saw. Yeah, so what will this become? What will this, or what will sigma Lk delta JL should become? What does this indicate? This indicates that this is equal to 1 only when j is equal to L. When j is equal to L, it has, 1 minute, j is equal to L, this is equal to 1. When j is not equal to L, this becomes 0. So sigma Lk delta JL can be written as sigma, no, j, when j is equal to L only, this will have a value, or else it will not have a value. So when j is equal to L only, it has a value, or else it won't have a value. So L will be replaced by j, that's it. So this whole term sigma Lk delta JL will become sigma jk. Is that clear? Okay. If you have a doubt, you just write it down in your notebook, expand this, and you will understand. Because delta JL, see, this is again one of the operations which you will quite often do. When you multiply some quantity with delta JL or delta quantity, okay, since delta has a value only when these two are the same, immediately what you can do is go and replace, remove delta, go and replace, okay, this index with this index, right? So sigma jk. Extending my previous argument, which I am not going to repeat, epsilon ijk sigma jk is equal to 0. Okay. So when I do this, what is, I mean, you expand it, I am not going to do that now, I think it's quite simple now for you. Okay. When I do that, I get to the fact that sigma is a symmetric tensor, or sigma ij is equal to sigma ji. Is it clear? So sigma ij is equal to sigma ji. Okay. So what does it mean? It means that in the tensor sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, and sigma 33. Okay. This is what you have to define, and this is equal to this, this is equal to this, this is equal to this. Is it clear? Okay. So as I told you, it had lot of say simplifications using integral notation, and once such a derivation you go through it again, maybe you can go through it 2 or 3 times. Once you go through this derivation, okay, you will understand completely what are the operations you can do with integral notations. Okay. Patiently go through this and you will understand, then you will not have any doubts about integral notations. That's the reason why I did this. Okay. So with these two derivations, we move over to another important property, 2 more properties. See, the ultimate aim, before we go there, I mean, we will close this class by looking at the ultimate aim of what I am trying to do. The ultimate aim is to interpret results, whether it is design or manufacture or whatever it is. What is my ultimate aim? Now, all of us know that some tensile tests are done with different specimens, standard tensile tests are done, and you have what is called as an yield strength of the material, sigma y. Or in other words, what we find from tests is given by one quantity called yield strength of the material. The question is that, look, you have defined 9 quantities and called this by various names, say tensors and all that. Okay. Now, as a designer, my interest is to tell or to determine when my material will fail. That is my interest. You have given me 9 quantities here, but from the material result or test result, I have only one quantity. How am I going to link up this with this? Which of the 9 quantities I have to take? Or can you now combine and tell me what is that quantity which I have to take? That is the question. And that's what I'm going to answer in the next class.